The Sun. It's the single object that makes life possible for us here on Earth. But what if that steady golden star we depend on decided to change everything? Imagine just for a moment that the Sun suddenly doubled its size, not over billions of years like stars do naturally, but right now, a snap change. What happens to Earth? What happens to the solar system? The simple answer is total, instant catastrophe. But how does that destruction play out, hour by hour, across our cosmic neighborhood? Before we talk about the death of Earth, we need to talk about physics. When we say the Sun doubled in size, that simple phrase actually means two completely different things when you talk about space. We have to clarify what we're changing: the Sun's physical radius or its total mass. Let's break down those options. Option 1. The radius suddenly doubles, but the mass stays exactly the same. The Sun's mass right now is roughly 1 solar mass. If we keep that mass constant, but the radius doubles, the Sun is now much puffier and much less dense than it was before. Think of it like taking the material of a regular basketball and forcing it to fill a basketball hoop. The volume is much bigger, but the total amount of stuff is the same. This would radically change the gravitational pull felt on the Sun's surface. If a star expands, its gravity at the surface decreases because the surface is farther away from the center. Option 2. The mass suddenly doubles, but the radius also doubles as a result. This is the true cosmic nightmare. Stars maintain a delicate balance. The inward pull of gravity fights the outward push of pressure created by nuclear fusion reactions deep inside. If you instantly double the mass, you instantly double the gravitational pressure, pulling everything inward. To counteract that massive increase in gravity, the core fusion must speed up drastically, and the star must expand until a new balance is reached. This scenario, where mass doubles, forcing a dramatic increase in size and power, results in unimaginable chaos. We must use the second option, the double mass, double size apocalypse, because only that gives us the kind of immediate catastrophic power capable of wiping out our whole solar system right now. A doubled mass star, now a 2 solar mass star, doesn't just shine a little brighter, it produces far more energy because the core pressure is immense, driving up the rate of fusion reactions inside the core. Stars react to running out of fuel or having core instability by burning brighter and hotter. In this case, increasing the core pressure means the temperature skyrockets, making the reaction rate go up significantly. The outward energy pushes against gravity, forcing the star to expand until the energy lost from the surface balances the energy made inside. A 2 solar mass star burns its fuel at a staggering rate, and its luminosity, its total power output, jumps by a massive amount. The moment the Sun doubles its size and mass, the immediate effect we feel is the sheer light and heat radiation washing over Earth. The brightness we experience is determined by the star's total surface area and its surface temperature. A doubled radius means 4 times the surface area. The massive increase in fusion means the surface temperature and overall light output also climb drastically, likely increasing the Sun's luminosity by over 10 times, instantly. This immediate, violent flash of extreme light and heat is the first thing that hits us. Think about the Sun's current power output, 4 times 10 to the 26th power watts. Now multiply that by 10 or more, delivered instantly across the solar system. This sudden radiation spike is the starting gun for the destruction of Earth. It is the beginning of the immediate breakdown of our planet. What happens next is not measured in years or months, but in hours. We are talking about immediate planetary breakdown. We've set the stage for unimaginable heat. In the next section, we look at how Earth begins to burn hour by hour as this massive, fiery presence replaces our gentle Sun. We just confirmed that doubling the Sun's mass and size immediately ramps up its total light output by a factor of 10 or more. This burst of high-intensity radiation instantly targets Earth. We must now track the timeline of destruction hour by hour. In a few billion years, the Sun will naturally expand into a red giant, and that slow, natural expansion is predicted to heat Earth enough to boil the oceans, melt the surface, and end life long before the expansion peaks. But a sudden, massive burst of power 10 times greater means that timeline is compressed down from millennia to mere hours. The Earth will become hotter than Venus in minutes. Venus is the hottest planet in our system right now. A star pumping out far more power than the current Sun means thermal equilibrium is shattered instantly. We are talking about the surface temperature rising past the boiling point of water almost immediately. In the first hour, the primary challenge is the atmosphere. The atmosphere we rely on protects us from incoming radiation. But against a tenfold or greater increase in solar radiation, the atmosphere becomes both a shield and a victim. The sudden flood of energy slams into the outer atmosphere, heating it intensely. As the gas heats up, it expands massively, far more rapidly than normal. This expansion is so rapid that the outer layers will begin violently boiling away into space. The atmosphere, instead of expanding in a smooth, protective blanket, violently overpressurizes and is partially stripped away. In the next 3 hours, the oceans begin to boil. The initial heat pulse immediately raises the temperature of the land and oceans. Water absorbs heat much more slowly than land, but the sheer volume of extra radiation is overwhelming. Since the Sun is now producing vastly more energy, the temperature of the oceans quickly rises toward 100 degrees Celsius. As the surface layers boil, massive amounts of steam are vented into the already chaotic atmosphere. This atmospheric supersaturation traps even more heat, leading to an extreme runaway greenhouse effect. Within a few hours, the boiling becomes widespread, consuming surface water across the planet. Within half a day, about 12 hours, the atmosphere collapses completely. The combined effects of the initial thermal stripping and the mass injection of steam cause the lower atmosphere to enter a state of total chaos. The atmospheric structure simply cannot sustain the energy input. The Earth's surface pressure plummets as gases escape, leaving the surface exposed to even higher levels of intense radiation and the full, direct heat of the colossal Sun. The planet is now functionally sterilized, turning into a glowing, water-vaporized cinder. In the first day, the surface melts. With the atmosphere gone and the solar luminosity cranked up, the planet's surface material heats up to molten temperatures. Earth is now a lava world, visible across the solar system as a bright, glowing sphere. The process of gravitational collapse inside a star releases enormous energy in the form of heat. When that heat is violently dumped onto an orbiting planet, the surface transforms into a planetary sea of magma. This immediate surface catastrophe is only half the story. The Sun is now not only bigger and brighter, it's twice as heavy. That means gravity itself has fundamentally changed across the solar system. In the next section, we'll look at the orbital mechanics of this new reality and which of our neighbors gets swallowed first by the colossal new Sun. Now that the Sun has doubled its mass and radius, it is time to check on our neighbors. This new star is a red giant scaled up to terrifying speeds and heat. We must look at two distinct threats: the physical consumption by the doubled radius and the gravitational chaos caused by the doubled mass. First, let's track the physical reach of the expanded Sun. The Sun's current radius is 1 solar radius. Doubling that means the new radius is 2 solar radii. We look at the distances of the inner planets from the Sun. Mercury is currently closest, followed by Venus, Earth, and Mars. 1. Mercury. Mercury orbits the Sun at roughly 57.9 million kilometers. The Sun's current radius is about 700,000 kilometers. Even a doubled radius is nowhere near Mercury's orbit. However, a star that swells into a red giant naturally expands until it can engulf Venus and almost reach Mars. Our doubled Sun is now a 2 solar mass star, which means it burns its fuel faster, forcing a radical, quick expansion. If this sudden mass doubling initiates the red giant phase instantly, the physical radius quickly begins to grow far beyond just 2 solar radii due to the thermal pressure. If the radius swells up to just over 1.0 astronomical units, 150 million kilometers, the Sun consumes both Mercury and Venus. 2. Earth. Earth orbits at about 150 million kilometers, 1.0 astronomical units. For the Sun to physically consume Earth, its radius must swell past 1 astronomical unit. While a doubled radius, 2 solar radii, is still safely small, the immense increase in thermal pressure from the doubled mass will drive the physical expansion outward aggressively, possibly reaching Earth's orbit within months, or maybe even quicker given the immediate instability. Earth's fate is sealed by fire long before the sun's edge physically reaches it, but total consumption is inevitable. The most dramatic, instant threat comes from the doubled mass, gravitational changes affecting orbits. The orbital path of any object is dictated by gravity. Newton and Kepler taught us that the speed and path of an orbit rely on the mass of the central body and the distance from it. Gravity is the universal force holding the solar system together. Since the central mass has suddenly doubled, the gravitational pull on every orbiting body, from Earth to Neptune, has instantly doubled as well. What happens to Earth's orbit? For Earth to stay in its current 1.0 astronomical unit orbit, it would need to instantly double its orbital speed to counteract the doubled gravitational pull. Since Earth cannot instantly accelerate from 30 km per second to 60 km per second, it must respond to the stronger gravity by falling inward. Our orbit instantly becomes a steep, plunging ellipse toward the core of the newly colossal Sun. This orbital collapse is independent of the intense heat we discussed in the last section. The planet is now being burned and pulled toward its doom. What about the outer planets? The gravitational effects extend throughout the entire system. Planets like Jupiter, Saturn, Uranus and Neptune, which currently orbit peacefully, suddenly feel twice the gravitational force pulling them in. Their stable, comfortable orbits become stretched, plunging ovals. While Jupiter's distance is far enough that its ultimate consumption is unlikely, its orbital path is irrevocably changed. Gravitational equilibrium is broken. The outer solar system is thrown into chaos, setting the stage for a long, slow decay. The Earth's short, fiery existence is already guaranteed. In the final section, we calculate just how long our planet lasts before it is completely gone and what happens to the remaining solar system bodies over the grand cosmic timescale. The Earth is now a molten cinder being dragged toward a star 10 times brighter and twice as heavy as the one we knew. The question is no longer if Earth dies, but how quickly it is erased from existence. First, let's calculate the timeline for Earth's destruction, given the combined effects of heat and gravitational collapse. We established that within the first 24 hours, the atmosphere is stripped and the surface begins to melt due to the extreme radiation spike. The Earth is already uninhabitable, but it hasn't been physically consumed yet. The final act of Earth's survival hinges on the race between orbital collapse and solar expansion. 1. Orbital collapse timeline. Since the Sun's mass doubled, Earth is now locked onto a plunging spiral toward the Sun's center. Calculating the exact time this spiral takes is complex, involving the mechanics of constantly changing mass centers, but the collapse is rapid by astronomical standards. Instead of billions of years, Earth's plunge toward the lethal boundary, the distance where the solar expansion stops, happens over thousands of years, potentially much faster, depending on initial stability and the precise mechanics of the orbit. However, long before that final inward spiral is complete, the physical expansion of the Sun takes over. 2. Solar expansion. Timeline. A 2 solar mass star lives an extremely short, violent life. Stars run through their hydrogen fuel faster when they are massive because the core burns at a higher temperature and density. This means a 2 solar mass star exists in its current phase for only a few million years, an incredibly short time compared to the Sun's current 11 billion year main sequence. The star's sudden expansion into its new superluminous state means its physical radius is already aggressively growing. Stars swell as they consume the hydrogen in their core. Even the slower, natural red giant expansion of our 1 solar mass Sun would eventually reach past Earth's orbit. The sudden double-mass star will enter this expansion phase immediately and aggressively. How long Earth survives? Earth's existence is reduced to a maximum of a few million years. Within that timescale, the Sun's radius swells far past Earth's original orbit of 1 astronomical unit, physically consuming the planet, vaporizing any remaining material, and incorporating the elements into the massive star's outer layers. Earth is destroyed by being swallowed whole by the rapidly swelling, colossal star. Now we must consider the long-term fate of the rest of the solar system. The new sun's lifespan is dramatically reduced. It is consuming its fuel reserves at an insane pace, giving it a total life measured in millions of years, not billions. During this time, the sun becomes an incredibly bright, massive, and highly energetic red supergiant star. 1. Planetary alignment. The outer planets, Jupiter, Saturn, Uranus, Neptune, are now on unpredictable, stretched orbits. Jupiter and Saturn are massive enough that the new sun will not consume them, but the chaotic gravity will ensure their orbits cross, leading to eventual close encounters and gravitational scattering. Some bodies will be ejected from the solar system entirely. 2. Stellar death. Since the star lives fast, it dies young and violently. A 2 solar mass star typically ends its life not as a quiet white dwarf like our normal sun, but in a more spectacular fashion, although still not a catastrophic supernova, which requires 8 to 10 solar masses or more. However, even a star of this mass, having burned its fuel so aggressively, would undergo catastrophic core contraction and eventually leave behind a carbon-oxygen white dwarf. This white dwarf would be extremely hot and dense, shrinking down to roughly the size of Earth. 3. Final solar system. The colossal red supergiant star eventually shrinks down into this tiny, Earth-sized white dwarf. This sudden and final gravitational drop will again wrench the chaotic orbits of the remaining gas giants, scattering them further. The ultimate long-term solar system is an empty expanse of space, orbiting a tiny fading white dwarf, potentially with a few scattered gas giant planets or remnants that survived the orbital chaos. The entire solar system, built over billions of years, is fundamentally rewritten in just a few short million years by this catastrophic change. The forces that govern the birth and death of stars are truly massive. If you want to continue learning about the unbelievable environments that can exist in our universe, you should check out the possibility of worlds much larger than our own. Click here to see What If We Lived on a Super Earth video. I'll see you there.